Did you know that your commercial building is full of actuators? Actuators are used by a building automation system to control the temperature and ventilation in a building. Current building automation systems consist of digital electronics. Within the network, components talk to each other in terms of varying voltages and currents. But something more is needed to interact with the real world of air and water flow that is used to control temperature in the HVAC systems of commercial and industrial buildings. The devices that translate voltages into physical motion are actuators. Actuators take the place of somebody's hand to turn a handle on a valve or damper. All these devices need power to operate. But what happens if power fails temporarily? Until power came back on, a regular electric actuator would remain stuck in the same position in spite of the changing HVAC needs. What happens if an outside air damper remains stuck in the open position on a very cold day? The coils inside the air handler could freeze and break, causing extensive damage. Fail-safe actuators, on the other hand, return to a safe home position if the electrical power or pneumatic pressure applied to the actuator is lost. Such actuators are often used on crucial damper and valve applications that require protection from excessive temperatures, such as preventing coils from freezing or rooms from overheating. Back in the days when air-powered pneumatics ruled commercial HVAC controls, fail-safe protection was easy because pneumatic actuators are inherently fail-safe. Air pressure pushes on a diaphragm that compresses a spring and drives the actuator's pushrod. When air pressure fails, the spring automatically returns the diaphragm and pushrod to the normal home position. When electric actuators began replacing pneumatics, however, they had no inherent fail-safe return. To remedy that, concepts from the old pneumatic spring technology were used to make spring return fail-safe electric actuators. As an electric actuator drove a load, it also tensioned a mechanical spring. To maintain position, power had to be continuously supplied. When the electrical power failed, the spring would return the actuator to its home position. To make a fail-safe version of a particular standard electric actuator, however, the torque had to be essentially doubled to overcome the resistance of the spring in addition to the load. Spring return actuators have been around for a long time, and building specs sometimes still state that spring return actuators be used. But a newer, more convenient, more durable, more consistent, and more energy-efficient solution for electric fail-safe is to use capacitors instead of springs. Capacitors are electronic devices that store electric charge and require very little current to remain continuously charged whenever power is applied. When electric power fails, the charge in the capacitor is used to drive the actuator back to its home position. Capacitor-driven fail-safe models provide multiple advantages over spring-driven actuators. Capacitor-driven actuators usually have smaller cases, weigh less, and can attach to shorter shafts than bulkier spring returns. Capacitor-driven actuators provide switch-selectable, fail-safe, and power directions so that one model can easily be used for both clockwise and counterclockwise fail-safe applications without flipping over the actuator and changing the shaft clamping mechanism. Not only can a capacitor-driven fail-safe easily change directions, it might also be turned off if desired, such as for testing purposes. The easier installation of capacitor-driven actuators is further enhanced by a quick-release button or lever that allows easy manual positioning of the shaft. Spring returns, on the other hand, usually require a wrench to manually wind the shaft into position, if manual positioning is available at all. Spring returns typically drive much faster and with excessive torque during fail-safe mode, potentially damaging equipment, but capacitor-driven actuators provide consistent torque during fail-safe as well as powered modes. Although they have higher peak initialization currents, capacitor-driven actuators provide overall higher energy efficiency. Spring return actuators require extra motor torque to overcome spring resistance on every cycle, and they consume much more power just to maintain a stationary position. After all these substantial advantages of capacitor drive are understood, few people will still insist on specifying old-school spring returns just because that's the way it has always been done before. Capacitor drive is clearly the future of failsafe. For more information about fail-safe actuators and other related subjects, visit www.kmccontrols.com.